Hello.
Hey Tim, how you going?
Good.
I'm in WA right now.
Yes, I recall.
So it is currently 8:30 in the morning.
Oh, there's an 8:30 in the morning now.
That's all right. I mean, I was up this morning at 3.
Yeah, right. That'll do it.
Yeah. So
Hey,
it's
well,
like midday. Hello, Valentina.
I'm gonna be in the background trying to prepare teaching and listen to this. Sorry.
Okay, no worries. No stress. So Devesh, he's gonna talk for half an hour. And then after that we've got Yarn, right?
Yeah, and he should be available pretty soon. Yeah, I don't know. You might remember the email he sent where he specifically said he was unavailable at certain times.
Right. Yeah.
Are you happy to chair today, Glenn?
Oh yeah, I think it should be fine. I'm just in my hotel
Cool.
room and I can walk off afterwards.
I'll be running around after a little one this morning.
Oh yeah, you've got baby duty.
Yes.
I do not miss that.
Yeah. Hey, James.
Morning, how are you?
I'm good.
That's good.
You've got to decorate your office, James.
Yeah, it's a bit, I've got a nice periodic table here of
Oh yeah,
finite
yeah.
simple groups. I don't know who'd left that for me, but it's
Uh,
pretty
that
cool.
well, that was commissioned by Jackie Ramage a million years ago,
I see.
and then it was inherited by Aiden, um, and I guess Aiden just left it there.
Yeah. Oh, I'm keeping it here. It's pretty cool.
Yeah, you're
I don't
definitely.
understand it.
Well, look, in Susanna's office, we have these mathematical artworks by
Oh
Escher.
yeah.
You know those Escher
Oh,
paintings?
cool. Yeah, why does she
So,
have that?
well,
Should be one of us.
they were they were like okay, so they're against university policy, if you can imagine the stupidity of that.
What?
But yeah, so the university has an art policy, and they went around to all the buildings in the university and just removed all the paintings and pictures from the walls of all the schools that weren't
Oh,
like aligned to the university art policy. And before they came around, we got a tip off, and so we took all the Escher things down so that they couldn't throw them away
oh,
and
good.
put them in the
Wow.
head of school office. But yeah, and so Susanna's just got them all now. I was going to like revive them and just I don't know, just like surreptitiously put them up there around.
Yeah.
That's also why the simple groups one is not on the wall because it used to be.
Ah, I see.
Yeah, how stupid.
Yeah. What's the so how do you make sure it's compliant with the policy? What's the
You
rule?
have to submit. Well, okay, there's obviously a ticket that you have to submit,
Of
and
course.
you have to get the correct approval from the correct a director of the art policy,
I see.
facilities management. They have to approve it, and then after they approve it, then you can put it up. But like, we were not able to get anything approved
Seems so
because
dystopian.
because every so they were like, oh, does the art have an indigenous perspective? And if it doesn't have an indigenous perspective, is it produced by a student or alumni of UOW? If you're
Ah, okay.
no to both, no.
Right. Interesting.
So I'm like, well, it's a periodic table of finite simple
Yep.
groups. I don't know.
You just need to get a student to draw on it, sign
I
their
had
Yeah,
name.
okay.
so one of my students made a whole bunch of Desmos pictures, and he got that on the wall, but it wasn't in our building. They approved it for engineering buildings, so that was on the wall for the engineering building. Look.
Oh well.
So anyway, I don't know how I got on this topic. Oh yeah, because James's office is all bare. Sorry, James.
Yeah. Yeah. No, you're right. I do have some stuff at home. I just haven't I literally forget to bring it in every time. I did this thing with some fellow postdocs where whenever we go to a conference, we would find the worst possible looking postcard, just the trashiest,
Oh
worst
really?
possible thing, and we would get that.
That's awesome.
Yeah. So I have a few of them I got to bring in.
I used to collect postcards when I was in my 20s, and then I stopped, but
Yeah.
it was fun.
Yeah, but it's fun
Um,
collecting the ugliest ones. But anyway, sorry, we should stop this off. Someone.
Yeah, Devesh, did you want to check if you can share your screen and stuff?
Yeah. Is it visible?
Oh, I got an echo. What's happened? Are you in the meeting twice, Devesh, or not? No.
I shouldn't be.
Oh, no, that's fine. You sound fine now.
Okay. The screen share stopped, right?
Oh, did you stop it or did it just do that by itself?
It crashed.
Okay.
It should be back now.
Yep, that looks fine. Are you ready to go or?
Yeah.
Okay, I'm going to start recording. Okay, welcome everyone to our next edition of our seminar series on Willmore and Willmore related things. We have, I guess, the conclusion, the exciting conclusion of Devesh's talk on Leon Simon's work, Existence of a Willmore Torus. Take it away, Devesh.
Thanks, Glenn. Yeah, this will be my final talk on Simon's paper, where he proves the existence of Willmore torus. This will be on the shorter side because I could schedule well. So there's only a few steps left in finishing the proof, and I think, yeah, this talk might be just around 30 minutes. But let's recap what we have done so far. So yeah, the setup is as follows. We have a smooth embedded surface in Euclidean space n Rn for n bigger than or equal to 3. We define the Willmore functional as a quarter of the L2 integral of mean curvature, where in my convention, the mean curvature is like the trace without averaging. Yeah. And yeah, the one important reason to study Willmore functional is that it's invariant under scaling translations, which are pretty geometric, but there's a bigger group, which is the conformal transformations, or the Mobius transformations of the Euclidean space. So it's invariant under inversion as well, where you like invert the sphere. So you can invert the spheres. And for a given surface, for a given genus G, let's fix this notation. So beta subscript G superscript N will denote the infimum of Willmore energy among all G genus embedded tori in the Euclidean space, among all G genus surface, sorry. And there are trivial bounds available to us, which is that this energy, this minimum, is bigger than or equal to 4 pi, but less than 8 pi. And we covered some parts of the proof why. So yeah, the main result here is that the minimizer is realized as a smooth analytic torus. Initially, Simon could only prove this in the genus 1 case, but there was a condition in his proof, which, if true, could be then the result could be generalized for arbitrary genus, and that's what Bauer and Court did almost 10 years after Simon's result. So the final result is that the minimizer is realized as an analytic surface for any genus. And this was the roadmap we were following. There were two ingredients before the before the GMT of the proof starts. We obtained diameter estimates via quite a clever monotonicity formula. And there was a technical graphical decomposition lemma which needed to be done. And once we had these estimates, we were trying to see how regular is the limit of a minimizing sequence. And the theorem proved by Simon is that it is analytic. It's as regular as it could be. But there is a possibility of genus loss. So if you start with a genus G minimizing sequence, in the GMT in the measure theoretic limit, the handles could shrink and you can lose genus. So this doesn't yet prove the existence of a minimizing torus. But there is a way to fix this, which is recall that our functional is conformally invariant. So we can perturb, we can change the sequence conformally and in a way to ensure that the limit doesn't lose genus and it is actually a torus. The last two talks, we were almost done with the measure theoretic limit part. We had proved regularity at good points. There was a classification for a given sequence between bad points and good points based on whether the curvature concentrates or not. Yeah, and I'll finish the proof of this part. The measure theoretic limit is analytic. And then we'll move on to the next bit where we prove that we have an actual minimizer in the Tori class. So yeah, this was a fun lemma. It is also of independent interest, which says that if I fix the area, then the diameter is bounded above and below by the Willmore functional. And this was important if you want to take a minimizing sequence. We observed that there are trivial bounds, upper and lower bounds for embedded surfaces. So if you fix the area, then the diameter is bounded above and below for a minimizing sequence, which allowed us to take the first part that at least measure theoretically there's a limit, which also lives in a compact part. The way to do this was there is a quantity gamma r which fell out of the proof, which looks like this. So for a positive real number, radius, the scale, there was a density part, area divided by r square, quarter of the Willmore functional, and there were some cross terms. This quantity turned out to be monotonic in R, and yeah, which later helped to establish diameter estimates. One important consequence was that if you push R to 0, you recover the limit pi coming from the area bound, area density. And if you push the limit to infinity, both these terms vanish. This goes to 0, the cross term goes to 0, and only the Willmore functional survive. So it reproves the trivial bound that your Willmore functional is bigger than or equal to 4 pi. And if you check the equality condition, you can also prove it's only attained for sphere. Moreover, we were doing this for surfaces, smooth surfaces, but it can be generalized for varifolds as well with density theta 2. There was another part, quite technical, which was the graphical decomposition lemma. So, which says roughly the following: if we have a surface embedded in Rn, and its L2 curvature at scale rho is bounded above by epsilon square, then the surface has good graphical decomposition. Yeah, picture explains 1,000 words. So here, the shaded region is my surface, sigma. And you can find planes, say in the picture, say L1 and L2, where the surface is graphical with small height and small gradient, except some small part, which are the pimples. And you can control the pimples nicely. The total diameter of pimples. Because Simon works in an embedded setting, he needs this, and a lot of other GMT tools to get to the regularity. Yeah, this was part of the proof. Yeah, and so this was the measure theoretic theorem, which we were 2 steps shy of proving. So I'm taking a minimizing sequence. So it converges. So the Willmore functional of the sequence converges to the infimum, and my normalizations are as follows. I am fixing the area to be 1, and it does all the surfaces pass through origin. Then the content of the theorem is there is a subsequence which converges to a smooth embedded surface. Um, there might be a genus loss. So if you start with a sequence of genus G surfaces, there might be a genus loss. But the limit is a minimizer in its class. So if the limit is of genus G naught, then it's minimizing in genus G naught class. Yeah, we needed a lot of lemmas before it. This this could be of independent interest too, which basically says the following. If I have a surface embedded in Rn, and near the origin, it almost appears like 2 sheets. So there are 2 disconnected components in the cutouts near the origin. Then the surface is not Willmore minimizing. So if double sheeted behavior appears, then there's a lower bound. So this rules out double sheeting when we go to the minimizing sequence. And yeah, so the Willmore functional detects the curvature nicely. The double sheets have low curvature, but the Willmore surface can detect that if the 2 sheets are close, then there must be curvature bending in some part, which which implies a lower bound.
Is
And
that
this
with,
can be, yeah.
is that with Liao? Is that how that works?
Yeah, so Liao proved
I
a
forget.
qualitative statement. Let's say this is a quantitative version. So
Mm.
Simon has a concrete bound, so 8 pi minus c beta theta. We are working in embedded surface. This can be seen as a quantitative version of Liao's bound. So it tells that you can actually compute the gap between 8 pi and your Willmore functional as well. The gap between 8 pi and Willmore functional is bounded above by c beta theta.
Yeah, that's
Yeah,
cool.
and Simon also says that this is a variant of Liao's
Oh,
inequality
okay.
in some
Okay.
sense.
Okay.
Yeah,
Thanks.
it's kind of a stronger version or a quantitative version of Liao inequality. Very interesting, and falls out of monotonicity formula.
I really think this sort of thing should be generalized. But anyway, this is kind of like you said, this is of independent interest. I think this is very cool. But anyway, yeah, good.
Yeah. There was another.
I was we're on asides. This reminds me of a tiny bit I knew about Almgren's big theorem, where he, as far as I recall, you end up getting minimizing submanifolds as looking like a pretty flat graph over its tangent plane, and you have to worry about double sheeting.
Yeah.
Yeah, so it's sort of looks having like it has quite a lot of similar aspects to it.
Yeah, I guess it appears in GMT in various areas. Like you want to avoid double sheeting or like multiplicity 1. You want to prove multiplicity 1 limits.
Yeah, it's a good comment. I think it reminds me of, yeah, I agree.
Yeah. Maybe it comes up with mean curvature flow too, but I haven't seen it in this way. Yeah, there was a fairly intuitive lemma that if I can represent my surface as a graph and it has small gradient, so du is pretty small, then the second fundamental form of the surface is comparable to the Hessian of the function. Because both of them are essentially two derivative quantities. And the small gradient lets you control it both way. We went through, there was a biharmonic comparison lemma, which says that you can, so if you have a graph, so if there's a plane in Euclidean space and the surface is parameterized by a graph of a function with gradient bounded, then if you solve the biharmonic equation along a boundary, then the Hessian norm of the solution is bounded above by this L1 integral, sorry, this line integral, so of the boundary value of the second fundamental form. Uh, yeah, it's used to create comparison surfaces. When we are going to take sequence, when we are going to have a minimizing sequence, this lemma comes in handy to create comparison surfaces and proves bounds later on. And not kind of technical, we can ignore it for now. So for the measure theoretic part, we divided the proof into 8 steps. The first was simple Hausdorff convergence part. Because we have diameter estimates, when you take a minimizing sequence and a monotonicity formula, you can conclude that the limit is not just a measure theoretic limit, but convergence improves to Hausdorff because the geometric setting comes from the fact that it's a Willmore minimizing, and Willmore functional is nice. Then we separated points in the Euclidean space based on whether there's a curvature concentration or not. Yeah, it might be good to recall the definition of bad point. Yeah. So, okay, yeah. So if sigma k is a minimizing sequence, by just measure theory, you can prove that there's a weak convergence of measures. Let's say sigma k as measures, as read-on measures, converges to a measure called, we denote by sigma, and a measure will denote the limit measure by mu and its support by sigma. And the job is to prove that the support is actually a smooth analytic surface. And for any point in the surface, we'll call it a point in the support is called a bad point if there might be a curvature concentration around that point. So this says that the limit of the second fundamental form near the bad point has a lower bound. And the way this happens is that if you have a sequence of tori which are getting thicker and thicker, and you can see that the limit will lose its genus. But at the origin, where the handles are coming in closer and closer, there's a high concentration of curvature. And so the origin will be a bad point in this limit. You can't avoid this because there is a potential genus loss. And there might be points where the sequence has high curvature. So yeah, this was the definition of a good point and a bad point. Yeah, a good point has the complement definition that there is no curvature concentration. Then we proved regularity at away from bad points, or we proved the regularity at good points. So if there's no curvature concentration along the sequence, with a lot of tools, with a lot of estimates coming with the help of graphical decomposition, we were able to say that, oh, the support is actually a smooth surface. So this was the content of these steps, 3, 4, and 5. You first C1 alpha. By decay estimates, you get C1 alpha regularity, and the fact that it's a surface. There's a PD result which improves the regularity to C2 alpha. This is special in 2 dimension. Once you have the C2 alpha regularity, There's a lemma by Simon that since we are at a minimizer, the surface will weakly solve a fourth order elliptic system, and the C2 alpha regularity improves to real analyticity. Willmore functional also follows lower semi-continuity. And so, now I'll talk about steps 7 and 8, which is that the limit we have obtained, which was just a limit of a minimizing sequence, is actually minimizing among its class, in its genus class. And we'll also conclude that the regularity holds at bad points, so the surface is smooth everywhere. Yeah. So this was the lemma by Simon where he improves C2 alpha to full regularity, to real analyticity, because we are in dimension 2. And so this is what we have so far. Hausdorff, measure theoretic convergence, real analyticity away from bad points, and lower semi-continuity of the Willmore functional. The lower semi-continuity also holds for if you replace mean curvature by second fundamental form, essentially by similar methods. You go in the setting of curvature varifolds. So now beginning the next parts of the proof. The varifold convergence, when you feed it back into the monotonicity formula, the problem at bad points was that the monotonicity formula was derived for smooth surfaces, so we couldn't feed bad points in a priori. But once we have proved the varifold convergence, you can use monotonicity formula at a good points and take the limit approaching a bad point, and this gives you a positive density. So even at bad point, the support at least measure theoretically behaves like a surface. It has a positive density, and it does not thin out a cusp at a bad point. There's also a part where you can control this integral, which says that it doesn't bend too much. The curvature, the surface doesn't bend too much at small scales, so it's approximately conical. This measures the defect to a cone, and at small scales, because of this, you can apply some averaging trick to say that on small scales, on annuli, this quotient, which measures the defect to the flatness in this case, is small, except for a set of measure also proportional to epsilon. The next step is that because of lower semi-continuity, we have gained something important, which is that the curvature, the L2 norm of the curvature, even around bad points, has an upper bound, which so compare it with the definition of a bad point. By definition, there might be curvature concentration along a sequence, but we have improved it that the limit still behaves nicely. Even if the sequence is concentrated, has a concentration, the limit is okay. The limiting the curvature norm at the limit. And again, what it suggests is that there is a genus loss happening at the bad points. Otherwise, there's no way the limit could have L2 norm bounded. And as I suggested, it's happening. So if you take a sequence of tori, which are thickening and thickening, and there's genus loss, the sphere still has bounded curvature, which is the limit. But the origin satisfies this.
Maybe I'll make a slight comment.
Yeah.
And that's actually the behavior that not Willmore flow, but well, it's conjectured for Willmore flow, but we see that behavior numerically for surface diffusion flow. So if you have a sufficiently thick torus, it actually does do exactly this. It thickens up
Oh,
into a ball and then breaks off like a whole
yeah.
cylinder. Yeah, it's really quite interesting. So it's not like
Yeah.
just a technical thing. Like this actually happens.
Oh, I see. Yeah. I mean, yeah, it would be interesting to do numerics, but yeah, this proof doesn't say what happens and what does not happen. What could happen? Yeah, so there is, if the genus loss happens, then it has to happen around bad points.
Yeah.
And yeah, a priori, there could be no bad points in some sequences. Then there's some technical part of the proof which says that your limiting surface behaves well over annuli. So script AI is an annulus around a bad point, and this tilde is like is a cylinder with bounded height over this annulus, and so this after some technical parts, technical proof, you can prove that it actually lies in this bounded cylinder. And this improves the limit. This proves there's a single sheet behavior even around bad points, because you can't violate the lower bound. Yeah, so piecing these things together, if we have a minimizing sequence and graphicality over the annulus near the bad points, we get uh, density convergence. What I mean by that is the Hausdorff measure was converging, but not only that, we have Hausdorff measure with density mean curvature as well as second fundamental form converging in the limit at good points. So recall, so far we have proved that our limit surface is smooth away from bad points. So it has a mean curvature and a second fundamental form. And this second fundamental form matches with the limit along the sequence. So the possible loss of energy is only at the bad points. Yeah, and this is the other part. So this semicon this is the other side of the lower semi-continuity. Here you prove upper semi-continuity to get equality. Yeah, and there's one more step remaining, which is that we haven't actually proved that the limit is minimizing in its genus, and you need to do a little bit of work for this. So if you take another surface of the same genus and near the bad points, after all the estimates, you can well approximate the surface and you can take out parts of your competitor, replace it with parts of the sequence here, such that if you do this cut paste process, you can ensure smoothness, and you'll create new competitors we'll call sigma k. So this is the competitor minus some balls where you have replaced it with cutouts coming from sequence and well adjusted so that this new competitor is also smooth. And recall that this was a minimizing sequence, so we have this inequality. The functional is bounded above by this new competitor plus some epsilon k going to 0. And if you do some algebra, the bad parts cancel out. This is the same as this. And what this actually implies is that the competitor must have more Willmore energy than the limit. And you need to take a sequence and The limit is well behaved because of the very full convergence proved earlier. And yeah, this proves that we are actually at a minimizer, and all we are left to prove is that it's smooth everywhere, including at bad points. And this part is easy. So once you are at a minimizer, you can reiterate biharmonic comparison lemma to get decay estimates even around bad points. So at small scales, around a bad point, you'll get some decay inequality. So here, the norm of the second fundamental form is bounded above by some power of the radius. And you can feed this decay inequality back into the previous parts at good points, like how we did at good points, and you'll get the estimate, and you'll get the same regularity. So first, these decay estimates gives you C1 alpha and W22 irregularity, which improves to C2 alpha, and then by two-dimensional results, this improves to real analyticity. So yeah, this completes major theoretic part of the proof. And our limit is genuinely a real analytic surface, and it's realized in its genus class. Okay, yeah, any questions so far? Or anything you'd like me to repeat?
I think people are happy.
I see, okay.
I guess.
Yeah.
Or they're stunned into silence.
Yeah, it's so powerful. You start only with the fact that you are at a Willmore minimizing, and it's a measure theoretic convergence. Somehow there's enough machinery and enough tools to give you full regularity at the end
Yeah,
with
it's
these very
remarkable.
basic
Yeah.
objects.
This is like elliptic regularity on steroids.
Yeah, exactly. Like you start with just measure theory and get the PD regularity with as much as you like the full regularity.
Yeah, it's amazing.
Okay, now we move on to the second part, which is preventing genus loss. And this is the theorem. So if I have a minimizing sequence of tori such that the there's a genus loss in the limit, so you actually converge to a sphere, then you can change the sequence a little bit by conformal transformations. Well, I'll call that sigma tilde. The sigma tilde also happen to live in the ball, and the sigma tilde converts to torus. There is no way you can have a sphere here as a limit. Yeah. So this is the inversion trick. If I have a surface, for any point not in the surface, let d sigma y denote the distance, and I'll create a set S epsilon, which are roughly the points in the surface which are close to y. So the distance from y to q is of the order of the distance, with the small factor to allow more points than just y. And if if the y is close to our surface, we'll consider this inversion trick. So x is inverted around y and then scaled by the distance. And we'll call this inversion by tilde. Here's the dichotomy Simon proves, and it's not trivial to observe even. If the diameter of the inversion has a lower bound of 1/4, then this inverted surface is some Hausdorff distance away for every round sphere in the ball. So you pick any point and you pick any small radius as that that sphere is contained in the ball, then there is at least some Hausdorff distance of this inverted surface from these spheres. And these are close conditions, so they survive Hausdorff convergence. And as you can see, the trick is going to be proving that such inversions exist. And if we can prove that such inversion exists, then we are guaranteed to be away from spheres. Like there's no way that if we take the limit of these inversions, we must have a torus at the end. And yeah, so this is the dichotomy Simon proves. Either your inverted surface is non-spherical, which I'll call this the non-spherical condition, or it satisfies an alternative. That diameter of the points near y is small, and for all points near the surface. Yeah, the proof the proof involves some topology, surprisingly, but it has to come like there has to be a way to detect the genus in order to do this proof, and Simon does it as follows. So if I have a torus, then there is a smooth map from n-2 sphere to the complement of the surface, which is not null homotopic. The easiest way to visualize this is codimension 1 case. So if you have a torus, there is a circle like this going outside, and there's a circle inside the torus, which cannot be null homotopic. I've created a visual as well. So yeah, this is your curve which lives outside the torus and is not null homotopic. And this detects, and since genus is non-zero, there has to be one such curve. And it also, this delta naught is defined as follows. So yeah, among all, so if you take a fixed map gamma naught, you consider its homotopy class, and you measure the distance the class have against the distance the class have with the surface. So it kind of measures the width of this gap. And yeah, and if you want to, you can also see it as the width of the handle in the complement. The complement will have a handle. So this big ambient space, and there's a handle coming from this section. It's the width of this, of half of the width. And the delta naught is realized here in by the curve which passes kind of far away from all the point, because we are taking a supremum here. And geometrically, if you have a fattening of torus, this delta naught has to go to delta naught has to become small, and this is how Simon detects the genus and the genus loss. Kind of amazing. So yeah, we are going to rule out the alternative. Recall that there's a dichotomy that either non-spherical, the inversion is non-spherical, or some condition holds which controls the diameter. Suppose the alternative holds and this width, this handle width is also small. Then Simon proves a homotopy which pushes gamma away from further from sigma, and it leads to a contradiction. So the alternative and small width cannot simultaneously happen. And we are almost at the proof yet. So if the width is small, then a good inversion exists. And here's the magic. A minimizing sequence of tori converging to sphere must have small width. Like if you have a fattening of tori, this width must be going to 0. So we are in the good situation. And since we are in the good situation, there exists an inversion which is non-spherical. And by taking the sequence, we are done. Like we have a limit torus at the end. Almost magical. But this step, ruling out the alternative, is far from trivial.
Yeah.
This
Yeah, like so how does that work actually? Like so what is the idea of this homotopy again? I forget.
what
Like what does the homotopy do? How does he build it? I forget.
uh, if the alternative happens, which is that the distances of all the points, it's kind of so. This is like we are near a flat part, and then this cannot happen. So if the diameter of the points which are on the surface close to y and are small has to happen near flat parts, and I think this along with the fact that the width is small creates a contradiction. You can't have small width near a flat part. But I haven't fully looked at the details.
Yeah, okay. No,
This
that's
is
all right. I was just
this is the
curious.
gist out of it.
Yeah, cool. Got it.
Yeah, and there's a contradiction coming from the homotopy. The But again, it's far from trivial how Simon does it. But once you rule out the alternative, yeah, small width implies good inversion, implies non-spherical limit. So yeah, voila, we are done, and we have the existence of a smooth Willmore minimizing torus. Yeah, before we're finishing the talk, let's look at what went on through the proof. We started with the minimizing sequence, um, and the limit we proved that the limit is analytic even if there's a genius loss. And the trick was that then the curvature concentration has to happen at bad points, and Handel might pinch off near bad points, which is what caused the genus loss. Conformal invariance led us to inversions which could prevent these genus loss. And in the genus 1 case, we knew about the existence of a non-null homotopic Sn-2 map, which along with small width gave us that a good inversion exists. This allowed us to create a new sequence which has to be away from spheres. And then going back to the previous measure theoretic limit, we arrived at the existence of a Willmore minimizing torus. Yeah, amazing proof. Um, I'll I'll finish the talk here.
Thank you, Devesh. I agree. An amazing proof in a very intimidating paper. So
Yeah.
congratulations on uh giving these talks.
Thank you for the
you did a great
challenge.
job. Yeah, you did a great job.
One of the most difficult papers.
Yeah,
I think
amazing
it's
work,
up there.
Devesh. Well done.
It's yeah.
It's up there.
Hmm.
We got any questions for Devesh? Any comments?
Devesh, do you know, did you look at Leon's 85 paper, the existence of Willmore surfaces? And
I didn't know about it. I started with this paper, but yeah, it turns out there was a precursor paper where he proves it in codimension 1 for surfaces in R3, which where some parts of the proof were simpler.
yeah, I was wondering. I mean, I
And
think
this was a
this one,
big gap in time between the papers. Like,
yeah, 85 to 93, yeah. Thanks.
yeah, well, it could be worthwhile to look at the simpler paper with hopefully simpler techniques and to see what's going on.
I'm not super familiar with it, but I think it's the same technique, but because
Okay,
it's a simpler setting, that it's much easier to read.
I
You could
see.
give another 5 talks on it, Devesh.
Oh, that's great.
No, I've done my duty here for the year.
Oh, if only every geometric analyst would give talks in our seminar each year, then we would be blessed. Okay. Well, if no further comments, then we'll thank Devesh again and thank everyone for coming to our seminar.
Thank you, Glenn.
Yeah, great work, Devesh.
Thank you, Matt. Bye. Bye. See you, Glenn.
I'll just stop
Thanks,
recording.
Devesh.